Hello and welcome back. We have actually seen the theoretical explanation of the stochastic gradient descent and how it can solve the memory issue and the dummy variable trap issue and the process issue. Let us try to understand the same with a intuitive example. On the dataset we have shown you, the 25 record dataset, we tried to generate these lines, how the algorithm is converging and how exactly the cost is changing, theta is changing. We have done it. So let us look at it and try to understand. So if you look at this, we are showing you on the left side the diagram. We are showing you the squared error and the slope. Right? When you see this, when you look at that, it is actually jumping. Right? It is actually the slope is going down and coming up, going down and coming up. If you look at it, try to observe that. Right? It's going up and down, up and down. By the time it reaches the fifth epoch, right? Here we are looking at second epoch and 25th, third epoch, and right, it's going a bit faster. And if you look at the theta, it is actually trying to converge, and it's almost converged by third epoch, right? When you look at the fifth epoch, right, you will see some zeros here on the slope. When we show 0, it is a rounded off value to 5 digits, and it may not be exactly 0. That's where it is still converging. If it is exactly 0, the convergence would have stopped. Okay, but you look at it, see that 0, right, like that. It actually reached the global minima, and still, right, when you look at this, it reached the global minima, and then still it is jumping around. That's what I tried to explain, right? The stochastic gradient descent reaches the global minima and will not settle at a particular theta, right? It is actually jumping around because you are passing one record at a time. The pattern understood is a little different from the previous one, so the gradient is going to change a little bit, and then the theta is going to change accordingly. But it stays at the global minimal place and jumps around. So with each epoch we are reducing, with each iteration we are reducing the learning rate, so that the jump size will reduce and it sticks to close to the actual global minimal error theta. So we are talking about global minimal, right? There will be local minimas here, right? When you see this curve here, you will have almost slope 0 kind of curves. If you look at this one, right, it is almost zero slope. If the gradient or theta comes and falls into this, right, stochastic gradient can help you. A stochastic gradient's jumpy nature, the cost function's jumpy nature, will make the theta come out of that pit. If you use the normal gradient descent or any other algorithm, right, there may not be that scope, right? So stochastic gradient descent's randomness, the cost function's randomness, helps you come out of the local minimas and reach the global minima. In the local minima, you will have high error, right? If you see here, the j of theta is going to be high, but here it is the lowest, right? It is the lowest error. We are not saying it is the zero error, because when you fit a line like this, right, there are data points somewhere there, and your predicted values are going to be on the line. So there will be error when you build a model. There will be error, but that error should be minimal, right? So this gradient descent algorithm or stochastic gradient descent algorithm helps you find the global minimal error place by playing with the theta. Okay, so if you look at that jumpy nature, it actually kind of showed you. See that 0, -6, 0, right? Fortunately, at the end it actually stopped at 0, but in some cases it may actually stop at some gradient also. If you look at this graph, right, this is the ultimate journey it made. The line started here, or theta started somewhere here, and then slowly it converged towards the global minima. And in between also, the jumps are big jumps sometimes and small jumps sometimes, because of the cost function's non-convex, strictly non-convex nature. This is happening. So let us try to look at the consolidation, or let us try to consolidate the algorithm. So SGD cost function is irregular, right? You can see that on data we have generated it on the 25 records. We have generated it and showing it. It's a real thing. We are actually looking at, right? And then because of that cost functions, now you can see that, right? Cost function is not strictly convex, and then because of this randomness, theta ends up close to the minimum, right? We have seen that here. It reached the global minimum and it is actually jumping around. When you see the gradient scores, it is jumping around minus maybe around 4000 to plus 4000 range. Okay, that's slope. Okay, so and the next point is the local minima and global minima. If you look at this place, right, it has got local minimas also. You can expand this and maybe can envision like this. When the theta when the theta calculated, if the theta falls here, right, the slope of the tangent here is 0. There is a danger that theta minus alpha into 0 is equal to theta, same theta. 5 is equal to the 5 minus alpha learning rate into 0 is going to be 5 only. If you run n number of iterations also, it may get stuck here if it is normal gradient descent. Because of the non-convex, not strictly convex nature of the cost function, the gradient is getting calculated different and it is coming out of the local minima and reaching the global minima. So this is called as global minima, where the error is the minimum, and these are called the local minimas, where the gradient slope is 0 but cost is still high. Okay, so that is the difference between local minima and global minima. And the randomness will help you in coming out of local minima and reach the global minima, but it is bad because it will not settle at a particular place. Once it reaches the global minima, it will not settle at a particular place. But the advantage here is that it gives you as good as the accuracy as good as the batch gradient descent. By saving, at the same time, it actually saves the memory and processing power. This is a big help when you are working with huge volumes of data, especially when you are building the deep learning models. This stochastic gradient descent is going to be very helpful. Okay, the randomness can be slowed by using a learning schedule, right? So with each epoch and iteration, you reduce the learning rate so that the jump is going to constrain to less area. If you keep the same alpha, the learning rate, the jump may be big and it may come out of this global minima and may jump into a local minima, or it may actually fall at a place which is far from the actual global theta. Okay, so that's the explanation about stochastic gradient descent. We have understood the most important two solvers, gradient descent, stochastic gradient descent, and we'll see a mini batch gradient descent here. That mini batch gradient is simple. Instead of taking one record at a time, you are taking bunch of records at a time. If you take bunch of records at a time, maybe 8 records or 16 or 32 records at a time, the pattern recognition is going to be more constant. The non-convex nature, non-strict convex nature of the cost function will reduce and it becomes a little more systematic. So we will use batch gradient descent a lot in our deep learning models than the stochastic. So that's about the theoretical understanding, and in the coming session we will understand practically how to use stochastic gradient descent using scikit-learn's module, and we will understand how to play with the hyperparameters like learning rate so that we can achieve the maximum accuracy within less time. Okay, so thank you.